Mr. Teacher, what happens to be the problem?
Oh, I have an issue on my hands.
What's wrong? Can I help you with it? I happen to be the brainiest student in the class.
I know, but I think this is one that only Super Nerd can help. You see, I have to teach the class about brain aneurysms, and I just don't know how.
Well, you may be in luck. I think Super Nerd may be close at hand, and with a few quick steps, I think we can call upon her. One moment, please. Now, sir, what seems to be the problem here?
Oh, I have to teach the class about brain aneurysms, and I just don't know how to teach the math to them.
Well, now, Mr. Teacher, you happen to be in luck. With my plethora of knowledge and my handy-dandy notebook, I think I know the math behind it. So you just go over there and grab that camera, and I'll show you the math. And I'm going to have you hold that camera right there just in case you forget. You can reference back to it. So, here we are. Get my handy-dandy chalk. The first thing you need to know is the radius of a normal blood vessel, which happens to be 0.01 meters. Now you plug this radius into the area equation. Area equals pi radius squared. So, area equals pi times 0.001 meters squared. Now this, remember, is the radius. Now, we get out our handy-dandy calculator, and we do all of that mathematics just by multiplying pi times 0.001 meters squared. And we get as our answer, area equals 0. Now count the zeros here. 0.00000031 meters squared. That's a tiny number. So that is the area of a regular vessel, very small. Now the next thing we need to know is we need to find the force on the outer walls of this blood vessel right here. So with this area we just calculated, we plug this in to the formula P, which stands for pressure, equals force over area. And this area is going to be what we just calculated right here. So then the normal pressure on a blood vessel is 1.0, oops, sorry, I made a mistake there, 1.6 times 10 to the 4th power. And then we're just going to solve for F. So F goes on the top, and the area we calculated, 0.00000000031, goes on there. Now this is just basic math, people. We're just going to multiply this unit right here by this one, using our friend the calculator. And doing that, we can find force. So it's just basic algebra. And force happens to be, let's see here, where is it? 0.0005 newtons. There you are. So now we have all the math on a normal aneurysm. Now comes the fun part. Now we're going to repeat this whole beautiful thing, but we're just going to be showing it when the aneurysm is all dilated from all of the problems that it's being caused. So, we calculate the area again. The radius, which is on this big, huge blood vessel right here, happens to be 0.5 centimeters. That's a whole lot bigger than the first time. Then we plug that into the A equals pi, and then plug that in for the radius, so 0.5 centimeters. And we plug it in to do solving on our calculator, and we find that A equals 7.85 times 10 to the negative 5th power. Now, we repeat again, and we use our little pressure formula. So pressure is still constant, so it's 1.6 times 10 to the 4th equals force Now this time, instead of using the area we calculated here, we use the area we calculated here for the dilated aneurysm vessel. So area equals 7.85 times 10 to the negative fifth. Now, we just solve for F by multiplying this by this, our calculator, and we find that F equals 1.26 newtons. Now you may be wondering and asking to yourself, so what, super nerd? What does that actually show? But if we look at the difference of this force and this force, that comes to a difference of 2,520% bigger. Now if you were that little blood vessel, I'm pretty sure you'd be popping too. So that is the science behind an aneurysm. Goodbye now.